Alright, so this is Mastering Physics, Chapter 12, Number 93. A cube of mass m slides without friction at speed v0. It undergoes a perfectly elastic collision with the bottom tip of a rod of length d and mass m equals 2 little m. The rod is pivoted about a frictionless axle through its center, and initially it hangs straight down and is at rest. What is the magnitude of the cube's velocity after the collision? So like we discussed in class, we can apply conservation of energy and conservation of angular momentum in this problem. So conservation of energy says the initial energy is equal to the final energy. And initially we have the cube, 1/2 m v initial squared, and that's going to be equal to the final, 1/2 m v final squared plus 1/2 I omega squared. So I omega squared gives you the rotational kinetic energy of the rod after the collision. So there's that piece. Now you also have conservation of angular momentum. So initial angular momentum is equal to final angular momentum. For the particle initially, you have m v initial times d over 2, and we discussed in class why the angular momentum of the particle initially looks like that. And that's equal to the same mass times v final times again d over 2 plus I omega for the rod. So then, I for the rod is equal to 1/12 times the mass of the rod, which is 2 times little m, times d squared. So that's equal to 1/6 m d squared. And that's little m d squared. So now let's substitute for I of the rod. You have m v initial d over 2 equals m v final d over 2 plus 1/6 m d squared times omega for the rod. If you solve, right, we can substitute, or rather we can divide every term by little m, and then you get an expression for omega. So algebraically, if you rearrange this equation, you get that omega is equal to 3 over d times v initial minus v final. So from this equation here, where we plug in for the rotational mass of the rod, the rotational inertia of the rod, we can find omega, the angular speed, the final angular speed of the rod. So now, going back to conservation of energy, we have 1/2 m v initial squared equals 1/2 m v final squared plus 1/2, and we'll go ahead and plug in. Now we know what I is, 1/6 m d squared times omega squared. So you have 3 over d times v initial minus v final, and all of that is squared. Okay. So now from that equation, what you can show, because, well, first of all, m's cancel, and what we want is we're solving for V final, right? So let's try to simplify all of this. We're going to get something that looks like V initial squared. We can take also a 1/2 out of each term. So V initial squared equals V final squared plus 3/2 times V initial minus V final, all of that squared. So if you rearrange this equation, what we want to do is make it look quadratic. So what we get is V final squared minus 6/5 V initial V final plus 1/5 V initial squared. So after distributing V initial minus V final quantity squared, distribute the 3/2, you've got this V final squared and V initial squared. After combining all of those terms, you get something that looks like this. V final squared minus 6/5 V initial times V final plus 1/5 V initial squared. And we use the quadratic equation to solve. You get V final equals 6/5 V initial plus or minus the square root of 6/5 V initial squared minus 4 V initial squared over 5 all over 2. Oops. All over 2. Okay. So if I look in this equation, using this as a quadratic equation, what am I solving for? Well, I'm trying to solve for V final. So V final would be like my x. So this would be like x squared, 6/5 times V naught. That would be the constant times x plus 1/5 V naught squared. That's the constant. So if I were to identify A, B, and C, A is equal to 1. B is equal to negative 6/5 V initial, and C is equal to 1/5 V initial squared. And so that's where we get this equation, applying the quadratic equation. A, B, and C are our coefficients. And then if you further simplify, you get two solutions. So one solution says you get 1/5 V initial. So V final is equal to 1/5 V initial. Turns out that is the solution, that you start out with V initial. Remember the mass? It has a collision, and it ends up with 1/5 of its initial velocity. The other solution is V initial. So that one is not the appropriate physical solution to this problem. That says that it doesn't change its velocity at all. And so that doesn't make sense in the context of this problem. It has a collision, of course it changes its velocity.